Today we're going to take notes on energy conservation and energy conversions. So energy conversion is the changing of energy from one form to another. So for an example, a car runs on gasoline, which is chemical energy, and it gets changed to mechanical energy, movement, and heat. Wind turbines take the mechanical energy of wind to spin the turbine and creates electricity. A tree takes in sunlight, which is electromagnetic energy, and that changes into chemical energy in the form of sugar. An atomic bomb takes nuclear energy and changes it into thermal energy or heat and the mechanical energy of the blast. Finally, a mixer that we plug into the wall takes electrical energy and changes that electrical energy into mechanical energy, the movement of the blade spinning, and sound energy, the noise those blade spinnings make. So the law of conservation of energy means that energy cannot be created or destroyed. It's simply going to change forms. So what that means is that our energy in the beginning should always match our energy in the end. So if we add math to this, we're going to say that our kinetic energy plus our potential energy in the beginning is going to add up to be our kinetic energy and our potential energy at the end. So the amount of energy on each side of our equation is always going to be the same. So let's try one of these out. A 50-kilogram skier glides down a frictionless hill of 100 meters, then ascends another hill of a height of 90 meters, as shown in the figure below. So we're going to graph at point A, that 100-meter hill, and we're going to graph at point B, that 90-meter hill. Remember, potential energy, or gravitational potential energy, is the energy due to position or height. So at that 100-meter hill, the skier is very high up, so we're going to say that he has about 10 blocks up of energy, of potential energy. Now, we're going to say at this 100-meter hill that our skier is not moving. Remember that kinetic energy is the energy of movement. So we're going to say at the top of this first hill, our skier has 0 joules of kinetic energy. But now our skier started to go down the hill. So let's look at point B. He's gone down the hill and back up again. Now at point B, he's not as high up. He's only 90 meters up. So we're going to say the potential energy is about 9 blocks up. But because energy cannot be created or destroyed, the amount of energy in the beginning, point A, needs to equal the amount of energy at point B. So we need to have 10 total blocks of energy here. So that means that our skier at point B must be moving. He must have 1 block of kinetic energy. So if we look at our graph from the beginning to the end, the total amount of energy needs to be the same. So if we took our kinetic energy from B and stacked it on top of our potential energy, it ends up being that same height as our potential energy because we had no kinetic energy at point A. Energy has not been destroyed, it just changed forms. Let's look at another example of this. At a ball rolling down a hill, back up a hill at multiple different locations. So we're going to start at point A. We're going to say the ball is not moving. It's the highest the ball is going to be, so the ball has the most potential energy. And we're going to say at point B, the ball has gone halfway down the hill, so the amount of potential energy has been cut in half. Now, going from 2 meters to 1 meter, again, that's half. So we're going to say it has half again as much potential energy. Finally, at D, it's reached the bottom, so it has no potential energy. Going back to point A, we know that it is not moving yet, so it has no kinetic energy. But at point B, we need our 2 bars to add up to the same as A. So we're going to say it's half kinetic energy and half potential. Point C, we now have more kinetic energy than potential. And at point D, we have all kinetic energy. We have all energy of movement because we had no potential energy. Notice that in each graph, all the bars add up to the same. Now, looking at the ball going back up the hill, notice that point A and point F, they have the same height. So our graph for A will also be the same as F. And our graph for E will be the same as B because the balls are at the same height.